exactly K. So similarly, in a similar line, we have the definition of edge connectivity, where we talk about the disconnecting set. So it basically a set of edges whose deletion creates more than one component. And also we discuss what is edge cut, where basically it will create exactly two components, and edge cut is called as minimal disconnecting set. And the smallest disconnecting set is basically gives you or I should say the size of the minimum edge cut or the size of the minimum disconnecting set that gives you the edge connectivity. And we have proven few theorems on connectivity of hypercube, and we has few interesting results like delta G greater than equal to chi prime G and not chi, sorry, delta G greater than equal to kappa G, kappa prime G and kappa prime G greater than equal to kappa G. So this is vertex connectivity less than equal to edge connectivity less than equal to the minimum degree of a graph. So today we will characterize two connected graphs, okay, and then we'll characterize in general k connected graphs. So what is two connected graphs? So before we go into that, first we say that what is internally disjoint path. So two paths from vertex U to vertex V are internally disjoint if they do not share any vertex. So say for example, if you like this one, U to V is one path, UWV is one path, this lower path is also another path. So they are vertex disjoint. So no vertex in the path are being shared. Now, Whitney in 1932 characterizes the two connected graph as follows: a graph G having at least three vertices is two connected if and only if for every pair UV of vertices there exists internally disjoint UV paths in G. Okay. So what? So a graph with more than two vertices is two connected graph if and only for each pair of vertices U and V we have at least two vertex disjoint paths or internally disjoint paths. Okay. The both things are actually same. Now this is Whitney's theorem and we will going to prove it. So if part, if we prove, so if part says that if for every pair of vertices U, V, we have at least two internally disjoint paths, then it is two connected. So this is very easy to prove because take any two vertices U, V, and since there is at least two vertex disjoint paths, so deletion of one vertex cannot disconnect the graph. So suppose I delete W, it cannot disconnect UV. So it is a very straightforward thing, the if part. So suppose you took any pair UV, there exists internally disjoint UV paths in G. Now you delete any vertex of any one of this path, but that doesn't make UV unreachable from V. So it's two connected. The proof of the other direction is good, so it's challenging. So the thing is, it says that suppose a graph is two connected, and we have to prove that we have at least two internally disjoint UV paths for all pair of vertices UV. So suppose it is a two connected graph, and we take any two vertices UV, and we prove by induction on DUV, that is distance from U to V, that the graph G has internally disjoint UV paths from every pair UV of Vg. So our induction parameter is DUV. Now, so suppose if DUV equal to 1, what happens? If DUV equal to 1, it means that U and V are adjacent to each other. So the graph G minus UV means from the graph we have deleted the edge UV. But since we delete the edge UV, we do not delete any kind of vertices. That means earlier it was 2 connected, now it also be 2 connected. So since G minus UV is connected graph, and since chi G, that is, so chi G greater than equal to 2, so vertex connectivity greater than equal to 2, and we know that chi prime G greater than equal to chi G. So यहाँ पे what I have reduced, I haven't reduced any vertex. I never delete any vertex. I have deleted an edge. So there is no question of so since number of vertices doesn't decrease, so chi G so basically, if you delete one edge UV, you always get an second path from U to V. An internally disjoint UV path in G minus UV always exists apart from the edge UV itself. And this is because of the definition of chi G. So chi G says that if I delete any edge, if I delete any edge also, if I delete the edge UV, then always I have another path from U to V. Now we have to prove it. So what is the induction step? So I will go here. So for DUV equal to 1, the base case is being proven. Now we assume that this is true. This theorem statement is true for all I, where I is less than equal to k minus 1. Okay. Now we have to prove it for DUV equal to k. So what is DUV equal to k? That is distance of U to V is k. And let W be the predecessor in the shortest UV path. So there are 2 UV paths. इसमें कोई एक path shortest होगा. If both are same, then I will randomly choose any one of them. And W is the predecessor vertex in this path. So what is the length of DUW? Definitely DUW is equal to k minus 1. And it is true because we have taken the shortest path. Applying induction hypothesis, we can say that there are at least 2 vertex disjoint paths between U and W. Now, so U and W means there are 2 vertex disjoint paths. मुझे प्रूफ करना है कि U and V के बीच भी 2 vertex disjoint path exist करता है. Now there are several cases appear. So नहीं मैं इसको रेफरेंस करके बताता हूँ. Then it will be so. Okay, I will repeat. So basically DUV equal to k, that is UV के जो shortest distance है, that is k. W is the vertex which is predecessor in this shortest UV path. So DUW का length होगा k minus 1. Now since DUW k minus 1, we can directly apply the induction hypothesis and we can say that there are at least two vertex disjoint paths between U and W. Now the thing is, एक path होगा U2W this, another path is UVW. Okay, so and it is possible in the first case. So if V, so here we use a notation V of path. So V of path means all the vertices that are in the path. Okay, V path actually means that all the vertices that are in the path. Now case 1 is if this V, so basically what we have to say, the UW के बीच में 2 vertex disjoint path exist कर रहा है. Suppose these 2 vertex disjoint path are P and Q, and V belongs to VP union VQ. That means UW path में in this picture V नहीं है, but UVW इस path में V exist कर रहा है. So if this is the case, then we can say that U and V के बीच में 2 internally disjoint path exist कर रहा है. एक है UWV and another is this UV. So basically what I am saying कि UW के बीच में जो 2 vertex disjoint path था, from that in fact I can derive 2 vertex disjoint path between U and V. So UW के बीच में vertex disjoint path कौन सा है? ये green वाला है. This is one path, so maybe I will okay, and the second path is UVW. Now since V belongs to this path itself, so UV में भी 2 vertex disjoint path है, एक है UWV, another is UV. This is an easier case. The second case is it may so happen this V doesn't belong to 2 vertex disjoint जो UW path है. The first UW path is P and the second जो UW path है, इसमें V doesn't exist. Okay, so there are 2 cases possible. Okay, so then what I am trying to say here, okay, so what I am saying, okay, there are 2 vertex disjoint path UW, but this is P and this is Q. Now V doesn't belong to any one of this path. That is the case 2. Then what happens? And so this is the case. Now we know. So what is given to us? So given to us is we have so it is a 2 connected graph. So there, that means UV के बीच so V doesn't belong to VP union VQ. Since G is 2 connected, G minus W, अगर मैं W यहाँ से delete कर दूं, then also U and V won't be disconnected because it is a 2 connected graph. If I delete W, it will remain connected. U and V will remain connected. Now what can be that? So that means there is a path between U and V, and that path could be like this. Okay. So that path may be like this. So if this path is totally disjoint from all these vertices, then we are done. So what I am saying, the first case, what was our first case? Our first case was that V belongs to either in path P or in path Q. Here it is, suppose here this V belongs to path Q. So what is path P and path Q? Path P is a vertex disjoint path from U to W. Q is another vertex disjoint path from V to W. Yes, so U to W. Now this on this Q path if V exists, then V के लिए हम two vertex disjoint path निकाल सकते हैं, एक है UV, एक है UWV. That is case one. The second case is V doesn't belong to this union. So in that case the picture look like this. U to W one path है. There are two paths, this green and suppose WV is connected because UV shortest path में suppose UWV this is the shortest path and W is the predecessor vertex to it. So ये length है k minus 1. Now since it is a two connected graph, if I delete W, then also U and V must be connected. That is definition of two connected graph. That means there is another path R between U to V. Now how this, so it may so happen this R is totally vertex disjoint from these two paths, P and Q path. In that case, we can say that between U to V, we have two vertex disjoint paths. One is UWV, another is this path R itself. Okay. So here basically two UV paths exist. One is UWV path. UWV path, and the second path is the totally vertex disjoint path, that is the path R. Path R. So this is my path R. Straight. You will name R. This is one case. Another case, maybe UV के बीच में जो connection है, W, if I delete W, U and V are not disconnected. But that does not mean this R path is totally vertex disjoint or internally disjoint path. It may so happen that it crisscross with this vertex. So that is the important case. So suppose this path is like this. So this is UW path, this is another UW path, and V is not a part of any one of this P and Q, and UV के अंदर since if I delete W and V are not disconnected, that means there is some path like this. Okay, and definitely these paths are not vertex disjoint. So in that case also I can create two paths between U and V. Two internal disjoint. One path is, this is my P path from U to W. U to W this is the P path and U to W this is the Q path. So ये जो path R है, this R suppose intersects either P or Q lastly at Z. यहाँ पे P में वो intersect किया Z में, उसके बाद there is no overlapping. So one path will be U to Z of the path of the P path के U to Z part we will take, and Z to V this Z to V R path का मैं लूँगा. So there are two UV paths. One is UZ path, UZ portion of P path and ZV portion of R path plus ZV portion of R path. And another path is I will take that UW path, that is total Q path, followed by the edge WV. So basically UWV path. So here I have shown you the two disjoint paths. So that is how we prove that if a graph is two connected, if a graph more than two vertices is two connected, then for every pair of vertices UV, we have at least two vertex disjoint or internally disjoint paths. Now characteristics of K connected graph. So suppose you are given a graph G, it has a vertex set V and a set E, G equal to V kind of graph, and you take any two vertex X, Y between them. Now a set S, which is a subset of Vg minus Xy, is called an XY separator or XY cut if G minus S has no XY path. Okay. So basically you are taking two vertices in a graph and you say what is an XY separator? A subset of vertices in the graph which separates X and Y. Okay. Now the minimum size of this set, so Vg minus Xy, there can be different options for choosing the S. The minimum size of this set is called minimum XY separator, and this can be represented by kappa XY. So kappa XY denote the minimum size of an XY cut. It is not the cut of the graph. It is saying the XY cut. Given any two vertex X and Y in the graph, what is the minimum set of vertices whose deletion separates X and Y? So the minimum size of that is called the so the minimum size is represented by kappa XY, and lambda XY is the maximum number of, so basically lambda XY give the maximum number of pairwise vertex disjoint or internally disjoint XY paths. Now Mengers proves the theorem that if XY are any two vertices of a graph G and Y X and Y, there is no edge between X and Y, in that case kappa XY is equal to lambda XY. Okay. Now, and what is original kappa? Original kappa is the minimum kappa XY for all XY belongs to VG. So kappa is called the vertex connectivity. So what is the vertex connectivity? जितने भी kappa XY होंगे उसमें जो सबसे minimum होगा, that will give me by kappa. So kappa is basically the vertex connectivity is equal to minimum XY cut, where I will take all pairs of X and Y's. तो ये थ्योरम हम लोग यहाँ पे प्रूफ नहीं करेंगे, एंड द रीजन इज एज फॉलोज. दिस इज ए वेरी इंपॉर्टेंट थ्योरम, बट जो प्रूफ इसमें है आपके डॉगलस वेस्ट में, वो प्रूफ थोड़ा सा रॉन्ग है. मतलब एक केस है जहां पे ये प्रूफ करेक्ट नहीं हो रहा है. सो दैट इज व्हाई आई एम नॉट discussing that proof here, because there is a problem in the proof. There are 4 cases, I think. The 4th case में कुछ proof में problems है, बाकी चीजें तो ठीक था. But it is a very important theorem, Menger's theorem, which says that if you take any two vertices in the graph, if you are taking any two non-adjacent vertices in the graph, then the minimum size of the XY cut is equal to the maximum number of pairwise vertex disjoint XY paths. Okay. So say for example, जैसे यहाँ पे देखो kappa XY equal to 4. So this is X, this is Y. So यहाँ पे 4 disjoint path मुझे मिलेंगे. So lambda का वैल्यू होगा 4. एक है green path, then second is this orange path, third is this red path, and fourth is this blue path. And if you see that chi xy is also 4, तो इस पाथ से मैं d को लूंगा, इस पाथ से मैं z को लूंगा, इस पाथ से c को लूंगा, एंड x w b y इस पाथ में b को लूंगा. So kappa xy equal to 4. So this red colored vertices. Okay, and also we see that the lambda xy, what is lambda xy? Lambda xy is the maximum number of pairwise vertex disjoint path. So minimum size cut जितना होगा उस same size का same number of pairwise vertex disjoint path मुझे मिलेंगे at most. Okay, जैसे सेम ग्राफ में मैं दिखाया हूँ कि जैसे यहाँ पे एक्स वाई का कप्पा था 4, फिर अगर मैं डब्ल्यू जेड चूज करता हूँ देन कप्पा एक्स वाई कप्पा डब्ल्यू जेड इक्वल टू 3. So one path is like wxz, it may be wxdz also, that is also valid path, but I choose any one of them. Then one is wcz directly and this is wbyz. So these are the three vertex disjoint paths, and if you see these red vertices, they are basically say the wz separator. Okay, so this is a famous theorem, Menger's theorem, and so actually Menger's इस theorem के Menger's ने जो theorem prove किया, इस theorem के basis से ही Ford Fulkerson ने actually they have devised that devised the algorithm for max flow min cut. Okay, so जो max flow min cut के जो idea Ford Fulkerson को मिला था, that is from this Menger's theorem. So Menger has a very important role in discovering different solution to max flow min cut problem. Okay, and we will discuss different variants of it maybe from the next class onwards. Okay, max flow min cut के different applications क्या है, उसके different variants of the problems क्या है, we will discuss those things. So next class से पूरे जो भी discuss करेंगे वो पूरा ही होगा algorithms. Now there is an important concept that is the line graph. What is a line graph? Basically, if you look into this picture, suppose this is the graph, then इसके corresponding line graph है this. So line graph क्या होता है कि every edge in G will be represented as a vertex in the next graph. जैसे E is an edge, E is a vertex. F is an edge, F is a vertex. H is an edge, H is a vertex. G is an edge, G is a vertex. Now E and F, these two edges are adjacent. So E and F, there is an edge. EG, there is an edge. FG, they are adjacent. So FG के बीच में एक edge है, FH के बीच में एक edge है, और HG के बीच में एक edge है. So the line graph LG of a graph G is the graph whose vertices are the edges of G. Whose vertices are the edges of G. Like F, E, G, H, these are the edges of G. They are vertices here. With EF belongs to, so EF जो edge है in this line graph, it is possible if E equal to UV in original graph G and F equal to VW in original graph G. That means they shared a common vertex V here. That is why this EF edge has been created. Okay. Now, तो हम लोगों ने कुछ देर पहले जो पढ़ा वो कैरेक्टरिस्टिक्स ऑफ K connected graph. So K connected, when I am saying like it's K connected means it always talk about the vertex connectivity. Similarly, another characteristics of K connected graph is if X and Y are distinct vertices in a graph or a digraph, then chi prime xy is equal to lambda prime xy. Now what is a chi prime xy? Chi prime xy is basically if xy are two different vertices in the graph, then a subset of vertices EG is a xy disconnecting set if G minus S prime has no xy path. So basically, and the size of the minimum set of edges, deletion of which disconnects x and y is called chi prime xy. So chi prime xy is the minimum size of xy disconnecting set. So it is basically a set, the xy disconnecting set. And lambda prime xy is the maximum size, I should say maximum number of pairwise edge disjoint xy paths. So let's see, मैं पिछले ग्राफ को कॉपी करके देखता हूँ क्या हो जाता है. तो काई प्राइम इक्वल टू लैम्डा प्राइम, तो यहाँ पे जैसे हम लोग दिखा रहे हैं कि यहाँ पे काई प्राइम एक्स वाई क्या होगा, व्हाट विल बी आवर काई प्राइम एक्स वाई. सो एक्स वाई के बीच में, एंड इट्स काई प्राइम एक्स वाई मीन्स minimum number of edges that will disconnect the graph, and lambda prime xy is, so basically they say that chi prime xy equal to lambda prime xy. So this is an edge disjoint path, suppose. Now this one is edge disjoint, then this is also edge disjoint, then this is also disjoint. Chi prime xy is also 4. So basically we have to say that अभी हम लोग so what are the edges that I may delete? So I can delete these edges, say this one, this one, this one, and this one. If I delete these 4 edges, that is why I am saying lambda xy equal to 4, right? So okay, so if I delete, say, or maybe I delete these 4 edges, or I may delete these 2 edges and these 2 edges, anything. So like this one, this one, this one, and this one. So maybe I make it bold, so maybe 3 points मैं इसको 6 point कर देता हूँ. If I delete these 4 edges, it says that these 4 edges actually create this xy disconnecting set. So minimum size of the xy disconnecting set is 4, and maximum number of pairwise edge disjoint path is also 4. And what about this wz? I think same ही होंगे यहाँ पे भी. तो यहाँ पे like if I delete this, no, I have to delete this. I have to delete this. Then maybe I delete this, and maybe I delete this. If I delete these three edges, W will be disconnected from Z. Okay. So basically what I'm trying to say, for any graph G, kappa xy equal to lambda xy and kappa prime xy is also equal to lambda prime xy. Now this is, yeah. So just say suppose if so we prove that kappa prime xy equal to lambda prime xy, यहाँ पे वही proof है. So what they have done, suppose this graph is given to us. Okay. Now, so so for this graph, we convert it into its corresponding line graph. Okay, say for each edge, I put these vertices and x and a are adjacent, so x a के बीच में एक edge है. जैसे यहाँ पे f and g they are adjacent, so f g के बीच में एक edge है, d f के बीच में edge है, then e f के बीच में edge है. So that is how. So c is adjacent to b, e, d and a both. These four things. So b, e, d, a. So iska line graph is this. Now suppose an edge disjoint xy path in G, the xy path in G becomes a vertex disjoint xy path in LG. That is possible through the observation itself. It is because of the definition of line graph. So एज डिसजॉइंट बात, अगर यहाँ पे कोई चीज एज डिसजॉइंट है, so it must be vertex disjoint in the corresponding graph. Like x y में यहाँ पे x a d f y and x b e, so basically x is this vertex. So यहाँ पे what I have done, actually x is this vertex and y is this vertex. Now to prove that kappa prime xy equal to lambda prime xy, what I have done is x and y both are vertices. All other things are edges. So what I do, we will add an extra edge here, and suppose this vertex is S source, and so x y के बीच में, and y is my target vertex, so y से मैं एक edge खींच लिया, and this is T. Say for example this is T. So basically this is not x, basically this is my Sx. S and x here they are vertices. A is edge, D is edge, C is edge. So ये थोड़ा सा आप लोगों को समझना पड़ेगा. Sx जो मैं इस पिक्चर में ड्रॉ किया हूँ, these two are vertices. Sx, y and t they are vertices. All other things are basically all other levels are for edges. So this is Sx and this is my y. An edge disjoint xy path becomes a disjoint xy path in LG. Now in this LG I get a vertex disjoint path. Okay, so we can say that kappa prime xy, so यहाँ पे kappa prime I should say kappa prime xy for this G is nothing but equal to kappa xy LG. So when I convert, so after this line, I can say that kappa prime xyg equal to kappa xy lg. And why that is so? because अगर ये edge disjoint xy path है g, that means kappa prime xyg, it became a vertex disjoint xy path in lg. So that is why it is kappa xy in lg. Now from Menger's theorem we have from Menger's theorem what we know. We know now I am audible.
Yes, sir.
Okay. So so here the proof is written here, like, so it was my original g. I will, from g I will create g prime by adding two new vertices s and t and two edges sx and yt. So that is something I done. Sx and yt I have added, and from this graph I create lg. Okay. Now this does not change chi prime xy and lambda prime xy, because s is adjacent to x only and y is adjacent to t only, but t is adjacent to y only. Now we can think of each path as starting from edge sx and ending at edge yt. So a set of edges that disconnect y from x in G, if and only if the corresponding vertices in LG prime is an SXYT curve. So basically what I am saying, that is the thing, an edge disjoint XY path in G becomes a vertex disjoint XY path in LG. That is something that is written here. Now, so if we here, so now from, so chi prime, what is chi prime? Basically it is edge disjoint path. So it becomes a vertex disjoint path in LG. Now from Menger's theorem we know that if it is a vertex disjoint path, then that is equal number of sorry so that is the maximum number of vertex disjoint path in the graph also in LG. Now if it is a vertex disjoint path here, then it will be an edge disjoint path here itself. So if it is an vertex disjoint path, so I think I have messed up something. I just with the notation I just messed up. So what is chi prime? Chi prime is basically minimum set of edges, deletion of which disconnect a graph. So basically chi prime xyg say that it is a disconnecting set of G. So minimum disconnecting set of the G, that is defined by chi prime xy. Now it becomes, now if it is a xy disconnecting set here in G, then it becomes a xy cut in LG. So from this line I can write this. Chi prime is basically the minimum number of edges, deletion of which disconnects x and y. So that is the xy minimum disconnecting set in G, and this equivalent to xy cut in LG. That means the minimum number of vertices if I delete in LG, that will disconnect x and y. So I can write chi prime equal to chi sx yt in LG. Now from Menger's theorem, I can write that chi sx yt Lg equal to lambda sx yt Lg. They are same. Now what is this lambda? This lambda says that it is vertex disjoint. So a vertex disjoint xy path. A vertex disjoint xy path in Lg becomes an edge disjoint xy path in G. So we can, from here we can write that so chi prime equal to chi equal to lambda. Now from here I can write that lambda sx ytlg is equal to lambda prime xyg. So so this is basically the number of vertex disjoint path from Sx to Yt. Now that is in Lg. Now इसका अगर मैं corresponding graph G देखूं, उसमें क्या होगा ये? यहाँ पे जो vertex disjoint path था वो हो जाएगा edge disjoint path. So number of vertex disjoint path in Lg equal to number of edge disjoint xy path in G. So with these three things, so first observation is a xy disconnect. यहाँ पे जो xy disconnecting set रहेगा, okay, that is the set of edges which disconnects x and y will be the set of vertices in Lg which acts as an xy cut. So chi prime equal to chi, and Menger's theorem says that chi equal to lambda, and this, that means that is the these are the number of vertex disjoint paths in Lg. Now, if these are vertex disjoint paths, that means equivalently they are edge disjoint path in G. So, since a vertex disjoint xy path in Lg becomes an edge disjoint path in G, so lambda sxyt is lambda prime. So, it says that chi prime xyg equal to lambda prime xyg. A equal to B, here B equal to C and equal to C equal to D, that means A equal to D. So that's pretty simple. So basically it says chi prime, this proves that this equal to this. Now with this we end the theory part of connectivity. Then हम लोग next class से we will start on discussing on max flow min cut and its different variants. Okay, so with this I end this chapter. This part is important because this will give you a prelude to max flow min cut, and those things also we will discuss later. कैसे हो रहा है ये, जैसे
Sir,
max.
what is the syllabus?
Sorry.
So what is the syllabus of end semester?
एंड सेमेस्टर जितना पहले से एंड तक जितना पढ़ाया गया तो था, पर मेनली आई विल आस्क एल्गोरिथम्स एंड देयर एप्लीकेशन इन द एंड से. मैं ये सो आई विल डिस्कस, मतलब आप लोगों को मैं बता दूंगा क्या क्या चीज रहेगा. डिटेल सिलेबस में लिख दूंगा, एक मेल कर दूंगा, वहां पे डिटेल टॉपिक वाइज मैं लिख दूंगा क्या क्या है क्या क्या नहीं है. मेनली एल्गोरिथम्स जितने भी हैं सब कुछ है सिंस द बिगिनिंग ऑफ दिस कोर्स. बट प्रूफ्स जो है मैं प्रूफ्स में थोड़ा सा कम कर दूंगा कि प्रूफ्स मिड सेम के बाद जो प्रूफ्स पढ़ाया गया वही रहेगा, मिड सेम के पहले जो प्रूफ्स है वो नहीं पढ़ाया गया रहेगा. तो मतलब मैचिंग के सब प्रूफ्स रहेंगे, कनेक्टिविटी के सब प्रूफ्स रहेंगे, ये सब रहेंगे. बट फर्स्ट सेमेस्टर में जो प्रूफ मैं पढ़ाया था वो प्रूफ एग्जाम में नहीं आएगा.
Okay, sir.
Okay, thank you, sir. With this,
Sir, how many chapters have you covered?
आई थिंक और एक चैप्टर कवर होगा, तो 5 चैप्टर टोटल कवर होंगे. इंट्रोडक्शन था, ट्री था, उसके बाद मैचिंग, कनेक्टिविटी, देन दैट क्रोमेटिक नंबर, कलरिंग, वो भी कवर करेंगे.
Okay, sir. Okay.
एक्चुअली बुक्स के बाहर कुछ एल्गोरिथम्स भी कवर करना है, इसीलिए थोड़ा सा क्योंकि पिछले जो बैचेस थे उसके फीडबैक कहते हैं कि थोड़ा सा और एल्गोरिथम घुसाइए, इतने प्रूफ्स पढ़ने बोर हो गया है एकदम. तो हमने ठीक है चलो नेक्स्ट बार एल्गोरिथम्स. इसके बाद जो भी डिस्कशन होंगे ना, मतलब मान लीजिए 90% आर एल्गोरिथम्स, so it won't be that problematic for you to understand. It's interesting. So Friday से हम लोग एल्गोरिथम से डिस्कस करेंगे. Okay, thank you.
Thank you, sir.